NEC Article 250.122b states that where a larger conductor is used for the branch circuit conductors, the size of the grounding conductor shall be increased to the size required for the branch circuit conductors. The reasoning behind this requirement is to ensure that the ground fault current path has a sufficient cross-sectional area to safely conduct fault currents without overheating. Using a smaller ground conductor than the branch circuit conductors could lead to several issues. Firstly, overheating. If the fault current exceeds the ampacity of the smaller ground conductor, it could overheat and become a fire hazard. Secondly, inability to clear faults. A smaller ground conductor may not have sufficient capacity to allow the fault protection device, or FPD, to clear ground fault. Thirdly, increased impedance. A smaller ground conductor has a higher impedance, which can increase the fault current and reduce the sensitivity of the FPD. Here are some examples of when a larger ground is required. One example is upgrading an existing electrical system from a lower amperage to a higher amperage. Another is using a larger conductor than specified because it is readily available or cost-effective. A third example is installing a new branch circuit with a larger conductor than the existing grounding conductor. Now, considering a specific scenario where number 6 conductors were used because number 8 conductors ran out. Since number 6 conductors are larger than number 8, a number 8 ground conductor is required as well. This is to ensure that the ground fault path has a sufficient cross-sectional area to safely conduct fault currents. In conclusion, while the increased conductor size in a case like this may not be to eliminate voltage drop, it is still a requirement under NEC Article 250.122b. This requirement is in place to ensure the safety of the electrical system by providing a safe path for ground fault currents. The ground fault path impedance needs to be low enough to facilitate the operation of the overcurrent protection device such as a circuit breaker or fuse. A higher impedance ground fault path will limit the current flow in a ground fault condition. This lower current might not be sufficient to trip the breaker or blow the fuse in a timely manner, increasing the risk of fire or electrical shock. The larger grounding conductor provides a lower impedance path. This is essential for quickly clearing ground faults and minimizing the duration of fault conditions. The National Electrical Code, or NEC, specifies minimum sizes for grounding conductors based on the size of the ungrounded conductors in a circuit. These requirements are based on the ampacity of the conductors and the need to safely carry fault currents. If the ungrounded conductors are increased in size, the grounding conductor must also be increased proportionally to maintain the integrity of the grounding system. The ampacity of a conductor is its current carrying capacity in amps. The NEC provides tables that specify the allowable ampacities for different conductor sizes and types. The grounding conductor must have an ampacity sufficient to handle the potential fault current. Overheating is a significant concern because excessive heat can damage the insulation of the grounding conductor and surrounding materials. This can lead to a breakdown of the insulation, creating a potential fire hazard or exposing conductive parts, increasing the risk of electrical shock. The increased size of the grounding conductor ensures that it can safely dissipate the heat generated by fault currents, preventing overheating. When a ground fault occurs, the fault current flows through the grounding conductor back to the source. The fault current magnitude depends on the system voltage and the impedance of the fault path. A low impedance ground fault path is crucial for quickly clearing the fault. If the grounding conductor is too small, its higher impedance can limit the fault current, preventing the overcurrent protection device from operating quickly enough. This delay can prolong the fault condition, increasing the risk of damage to equipment and injury to personnel. The overcurrent protection device, such as a circuit breaker or fuse, is designed to interrupt the flow of current when it exceeds a predetermined level. The NEC requires that overcurrent protection devices be selected and installed to protect conductors from overcurrents. The grounding conductor must be sized to ensure that the overcurrent protection device will operate quickly and effectively in the event of a ground fault. A smaller grounding conductor may not have sufficient capacity to handle the fault current, potentially causing the overcurrent protection device to fail to operate or to operate too slowly. Sensitivity of the FPD, or fault protection device, refers to its ability to detect and respond to low-level fault currents. A higher impedance in the ground fault path can reduce the sensitivity of the FPD, making it less likely to detect and clear ground faults. The increased size of the grounding conductor lowers the impedance of the ground fault path, improving the sensitivity of the FPD and ensuring that it will operate reliably. When upgrading an existing electrical system from a lower amperage to a higher amperage, it is essential to evaluate the existing grounding system to ensure that it is adequate for the increased current levels. If the ungrounded conductors are increased in size to accommodate the higher amperage, the grounding conductor must also be increased proportionally. This ensures that the grounding system can safely handle the increased fault currents associated with the higher amperage. Using a larger conductor than specified because it is readily available or cost-effective is a common practice in electrical installations. However, it is essential to ensure that the grounding conductor is also sized appropriately to match the larger ungrounded conductors. Even if the larger conductor is not required for the current load, the grounding conductor must still be increased in size to comply with NEC Article 250.122b. When installing a new branch circuit with a larger conductor than the existing grounding conductor, it is necessary to upgrade the grounding conductor to match the size of the new branch circuit conductors. This ensures that the new branch circuit has a dedicated grounding conductor that is capable of safely carrying fault currents. The grounding conductor must be connected to the equipment grounding busbar in the electrical panel. This busbar is connected to the main grounding electrode system, which provides a low impedance path to ground. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must be installed in accordance with NEC Article 250 to ensure that it provides an effective ground fault path. The grounding conductor must be installed in a manner that protects it from physical damage. It should be run along the same path as the ungrounded conductors and should be securely fastened to prevent it from becoming disconnected. The grounding conductor should also be protected from corrosion. Copper conductors should be used in corrosive environments. Aluminum conductors should be used with approved connectors and should be protected from contact with dissimilar metals. NEC Article 250 provides detailed requirements for the installation of grounding and bonding systems. It is essential to follow these requirements to ensure the safety and reliability of the electrical system. Improperly installed grounding systems can create a significant risk of electrical shock and fire. In a specific scenario where number 6 conductors were used instead of number 8 conductors, the grounding conductor must be sized based on the number 6 conductors. According to NEC Table 250.122, a number 6 copper conductor requires a number 10 copper grounding conductor. However, since the number 6 conductors were used, a number 8 copper grounding conductor is required. This ensures that the grounding conductor is capable of safely carrying the potential fault current. The NEC requirements for grounding conductor sizing are based on the assumption that the grounding conductor will be installed in the same raceway or cable as the ungrounded conductors. This is known as running the grounding conductor with the circuit conductors. When the grounding conductor is run with the circuit conductors, the impedance of the ground fault path is minimized. If the grounding conductor is run separately from the circuit conductors, the impedance of the ground fault path can be significantly higher. This can reduce the effectiveness of the grounding system and increase the risk of electrical shock. Therefore, it is essential to run the grounding conductor with the circuit conductors whenever possible. The NEC also provides requirements for the use of equipment grounding conductors and equipment bonding jumpers. An equipment grounding conductor is used to connect the non-current carrying metal parts of equipment to the grounding system. An equipment bonding jumper is used to connect different metal parts of equipment together to ensure that they are all at the same potential. These requirements are designed to minimize the risk of electrical shock by providing a low impedance path for fault currents. The NEC also addresses the use of isolated ground receptacles. Isolated ground receptacles are used in sensitive electronic equipment to minimize electrical noise. The grounding conductor for an isolated ground receptacle is isolated from the metal parts of the receptacle and is connected directly to the grounding electrode system. This helps to prevent electrical noise from interfering with the operation of the equipment. The NEC provides detailed requirements for the installation of isolated ground receptacles. In addition to the NEC requirements, there may be local codes or regulations that apply to electrical installations. It is essential to check with the local electrical inspector to ensure that the installation complies with all applicable codes and regulations. The electrical inspector is responsible for enforcing the NEC and other applicable codes. The inspector will review the electrical plans and inspect the installation to ensure that it meets all requirements. It is important to cooperate with the electrical inspector and to address any concerns or issues that they may raise. The goal of the electrical inspection process is to ensure the safety and reliability of the electrical system. Grounding is a critical aspect of electrical safety. A properly installed grounding system can protect people from electrical shock and prevent damage to equipment. It is essential to follow the NEC requirements and to consult with a qualified electrician to ensure that the grounding system is installed correctly. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. By following the NEC requirements and using best practices, it is possible to create a safe and reliable electrical system. The information provided here is for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work. When dealing with electrical systems, safety should always be the top priority. Remember to always de-energize circuits before working on them and to use appropriate personal protective equipment, such as insulated gloves and safety glasses. The electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself and others. By following these guidelines, you can help to ensure a safe and successful electrical installation. The NEC is a comprehensive document that covers all aspects of electrical installations. It is updated every 3 years to reflect changes in technology and best practices. It is essential to stay up to date on the latest NEC requirements to ensure that electrical installations are safe and compliant. The NEC is available for purchase from the National Fire Protection Association, or NFPA. It is also available online through various subscription services. In addition to the NEC, there are other resources available that can help you learn more about electrical safety. These resources include textbooks, training courses, and online forums. By taking advantage of these resources, you can increase your knowledge and skills in the field of electrical safety. Electrical safety is a shared responsibility. Everyone who works with electrical systems, from electricians to homeowners, has a role to play in ensuring that electrical installations are safe and reliable. By following the NEC requirements, using best practices, and staying informed about electrical safety, you can help to protect yourself and others from the hazards of electricity. Remember, electricity is a powerful force that must be treated with respect. Always take the necessary precautions to ensure that electrical work is performed safely and correctly. The size of the equipment grounding conductor is also determined by the size of the overcurrent protective device, such as a circuit breaker or fuse, protecting the circuit. NEC Table 250.122 provides the minimum size requirements for equipment grounding conductors based on the rating of the overcurrent protective device. In general, the equipment grounding conductor must be sized to carry the available volt current without overheating or causing a voltage drop that could prevent the overcurrent protective device from operating properly. In some cases, the equipment grounding conductor may need to be larger than the minimum size specified in NEC Table 250.122 to meet these requirements. For example, if the circuit is a long distance from the power source, the equipment grounding conductor may need to be increased in size to reduce voltage drop. In addition to the size of the equipment grounding conductor, the type of conductor used is also important. Copper conductors are generally preferred for equipment grounding conductors because they have a lower resistance than aluminum conductors. However, aluminum conductors may be used if they are properly sized and installed. The equipment grounding conductor must be connected to the equipment grounding busbar in the electrical panel. This busbar is connected to the grounding electrode system, which provides a low impedance path to ground. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must be installed in accordance with NEC Article 250 to ensure that it provides an effective ground fault path. The equipment grounding conductor must be installed in a manner that protects it from physical damage. It should be run along the same path as the circuit conductors and should be securely fastened to prevent it from becoming disconnected. The equipment grounding conductor should also be protected from corrosion. Copper conductors should be used in corrosive environments. Aluminum conductors should be used with approved connectors and should be protected from contact with dissimilar metals. NEC Article 250 provides detailed requirements for the installation of grounding and bonding systems. It is essential to follow these requirements to ensure the safety and reliability of the electrical system. Improperly installed grounding systems can create a significant risk of electrical shock and fire. The size of the grounding electrode conductor, which connects the grounding electrode system to the equipment grounding busbar in the electrical panel, is determined by the size of the service entrance conductors. NEC Table 250.66 provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. In general, the grounding electrode conductor must be sized to carry the available fault current without overheating or causing a voltage drop that could prevent the overcurrent protective device from operating properly. In some cases, the grounding electrode conductor may need to be larger than the minimum size specified in NEC Table 250.66 to meet these requirements. For example, if the grounding electrode system consists of multiple grounding electrodes, the grounding electrode conductor may need to be increased in size to ensure that all of the grounding electrodes are effectively connected to the equipment grounding busbar. The grounding electrode conductor must be connected to the grounding electrode system in a manner that ensures a reliable and low impedance connection. The connection must be made using approved connectors and methods. The grounding electrode conductor must also be protected from physical damage and corrosion. NEC Article 250 provides detailed requirements for the installation of grounding electrode conductors. Grounding and bonding are essential for electrical safety. By following the NEC requirements and using best practices, it is possible to create a safe and reliable electrical system.